Hi, welcome to 2.3 horizontal and vertical translations of functions. We're going to skip the success criteria for now. We'll get back to it later. We are going to begin with an investigation. So if you go to this, in the class notebook, if you go to this handout, you'll be able to click on this link and you can bring up the Desmos investigation that we're going to do. So I've already done much of the groundwork. I'll show you what it looks like. So if you click on that link, it'll bring you to Desmos and you will see pretty much this setup that I have right here. So we can see I have a black graph, f of x equal to x squared. Okay, that's been entered in. You can see the graph up here. I've also added two other functions. However, I haven't turned them on. They're turned off. So this one right here is basically f of x, which is x squared, and it's plus c. So I'm adding this c to it at the end. What I've also done in Desmos is I've allowed c to become a slider. And what that means is it's basically a parameter. And if I hit play on here, that parameter can move from +5 all the way to 0 and then to -5. Okay, I'm just going to stop it back at 0. Move that over. There we go. Okay. In the third line here, I have another function. When I've done with f of x, I've now subtracted d inside of x. So what that means is we've taken this function x squared and we're subtracting a d from x before it gets processed. Okay, I've created a slider for that parameter too. You can see d right here. We just hit play and d also goes from +5, then to 0, then to -5. Okay, so we'll stop that one at 0 also. Okay, if I want to see any of the other graphs, I can just turn them on by clicking on them. Okay, so the x minus d one is in green, f of x plus c is in red. Okay, let's go to the investigation page. So this is your handout for 2.3, horizontal and vertical translations of functions. Okay. So in this investigation, we want to see what effect c will have on a function. Okay. What this means is if I take a function, let's say it's x squared, and then I add a constant to it that can range from -5 to 5, I want to know how is that going to affect the graph. Okay. And what I would like you to write in here is, what do you think happens when c is greater than 0? What do you think the graph will do? And what do you think when c is less than 0? Okay. And then once you've done that, I would then like you to change the function. So right now we're doing x squared. You can go in here and you can change this to root x. So we have the square root of x. Okay. And then I would like you to go through and turn on your parameter c here and observe what happens to the graph. Okay. You need to turn also when you hit play for c, you should also have this one turned on as well. So we can turn off the main function. You can turn on this one, or you can leave them both on. It's fine. But what we're going to do is we're going to hit play on C, and you're going to see how the red function is going to move. So I'd like you to make some predictions about that. Okay, once you've done that part, we'll now go on to the second part. You can turn this one off here, and you can then turn this one on here. Okay. And we'd also like to go back to our regular function x squared. So we'll type in x squared. Okay, so now we're looking at what happens when we subtract d from x inside the function. Okay, so our base function is x squared, and now what we're going to do is we're going to be subtracting a parameter d, which can range from -5 to 5 inside for x. Okay, so basically we're creating this new function. So once you have this one turned on, you could then go to D here and you can turn this slider on. And as this plays, what it's going to do is it's going to create a new function, and I want you to observe it and make conclusions about when D is greater than 0, and then make conclusions about when it's less than 0. After you're done that and you know the effects of D, just play around with some other functions. Okay, go into here and change this to 1 over x, and then see what happens. Okay. All right, so what you can do right now is you can pause the video, and then you can go ahead and try to complete this investigation on your own. If at any point you're not sure what to do, you can just hit play back on the video, and I'll go through, and you'll be able to follow along. Okay, so I will see you in a few moments. You can go ahead and hit pause. All right, well, welcome back. We're going to get this investigation started. So we're first looking at the effects of adding a parameter c to a function. Okay, in our case, we're letting the function be x squared. So what we're doing is we're doing x squared plus c. Okay? We're letting c range from -5 to 5. Let's see what happens when c is positive. So I'm going to turn that one off. I'm going to turn this one on. F of x plus c needs to be turned on. And I can go ahead and hit play. Play for the parameter c. So I can see the graph is moving up, and at 0, it's back at 0, and then there it's moving down. So I can control this myself. So I could see when c is positive, it looks like the graph just shifts upwards. It's not changing shape, it just moves upwards. And I can tell by the vertex. Vertex moved up exactly what c is, exactly 5 units. Okay. If I allow c to become negative, then the graph moves down. And notice it went all the way down to -5 because I brought c all the way to -5. If I go back to 0, we see no change in the graph. F of x is the same as f of x plus c. Okay, so let's write down our findings in here. If c is greater than 0, the graph shifts up. It actually moves up exactly c units. So if I set this equal to, let's say 1, the whole graph moves up 1. Okay. You might say, well, Mr. A, it doesn't really look like it moved up 1 like for the other spots. Like I can see it at the vertex, but as x moves outwards, or as the graph moves outwards, it doesn't really look like it. Well, it actually is always a difference of 1. So let me plot a vertical line. We'll say x equal to 1. Okay, and you can see there is exactly 1 unit between the top point on the red graph and the point on the black graph. Okay. I can move this over. And notice the dots keep the same distance with each other as they move. It's exactly 1 unit. Okay, let's click on those points again. So I'm going to make this 3, nice whole number. I'll change that to 3. And then if I click on those points, you can see there's exactly it looks like there's exactly 1 unit. Oh, I didn't change C yet. C is still at 1. Let's move C to 3. Okay, I'm gonna have to go in there and change that to 3. And let's click on here. Now let me grab that point. There it is, 312. And then this point here, 39. So you can see there's an exact difference of 3. Okay, I can move this over and you can see those points hold the same distance apart. So there's always exactly 3 units difference. So when C is a positive number, the graph will shift up exactly what C is. Okay. So that's kind of cool. That tells me about this right here. This says that if I have any base function, it doesn't matter what it is, if I add C to it, it's just going to shift up C units. So it doesn't matter if this is a function that I already know how to do, or maybe this is a completely new one for me. I know that by just adding C to it, it's going to shift up C units. Okay, let's explore with a negative value for C. Let's move this down, -5. And we can see we do have that nice distance of 5 units. And as I move that through, you can see the 2 points, they're always 5 units apart. Okay. So we'll write in here, if C is less than 0, then it just shifts down C units. Should write the word units after this. We'll put it up there. C units. Okay, are these effects the same for other functions? So we just did it for x squared. Let's change this to a different one. Do we get the same effect? I'll change this to root x. And I'll hit play on my slider C. I'll hit play. And we can see all it does is cause a vertical shift of exactly C units. If C is negative, it goes down. If C is positive, it goes up. So notice we just kind of discovered something about functions and some transformations. So this rule is true. What we've concluded here, this is actually true no matter what. Okay, for any function, that's true no matter what. Okay. And notice C only affects the graph vertically. We call these vertical translations. Okay, let's go ahead. Let's just write that down right here. Are the effects the same? So does C have the same effect on any kind of function, whether it's root x or x squared? And we can say, yes, it is the same. So yes, C, we'll put some quotes around that. Yes, C has the same effect on f of x. Okay. All right. Okay, now we're going to look at a new one. So this new function, g of x, what it does is it takes f of x and it changes the input. Okay, so my base function is going to be x squared again, but difference this time is we're now taking d, which is going to be some number between -5 and 5. We're now using that to change the input x. So we're going to have x minus whatever d is. So that's going to play a role on the graph. So if you change the input before it gets processed, it's going to change the way the graph is going to appear. Let's go ahead. Let's see what happens with this one. Let's go back to x squared. We're going to turn that one off. And we'll turn that vertical line off too. And let's turn on f of x minus d. That's this one right here. I'm going to go ahead and hit play on the slider, and what that's going to do is it's going to change the parameter d. As I hit play, notice the graph just shifts horizontally, either to the left or to the right. Okay. It's to the right when d is positive, like I have over here. Okay, notice I set d to 5, and the vertex moved exactly 5 units. If I set d to -5, the vertex goes exactly 5 to the left. All right, let's check and see if this happens for other functions as well. Let's change the base to 1 over x. We haven't really done that one in a while. 1 over x, I'll go ahead and hit play. And you can see it's that function has those 2 branches, and it's exactly just sliding left and right. Notice the shape doesn't change, just its position does. All right, and you can see when d is negative, it goes to the left. When d is positive, it goes to the right. So it has the same effects. Let's go ahead and write some of this down. So we can say here, if d is greater than 0, so right now we're showing d as a +5. The graph shifts right 5 units. If d is negative, then the green graph moves to the left of the black one. We say it shifts left 5 units. And this is the same regardless of the type of function. Even if I do even a plain old simple boring y equals x function, we can still see it has the same effect. So what's interesting about this one though is it looks like it's actually moving up and down, doesn't it? However, moving up and down can also be perceived as going left and right. So right now the function is moving to the left, and then now it's moving to the right. So it actually, when you're working with the graph y equals x, a lot of the vertical and horizontal transformations can't be distinguished. They can appear the same. So taking that black graph and moving it to the right is going to look like it's moving down also. Okay, so that is it for our investigation. I'm just going to answer this last question. We're just going to say the effects are the same. So what that means is this parameter D inside here causes horizontal translations, shifting to the left or to the right. And the parameter C that's added outside of the function, that causes functions to shift up or down. And this is true regardless of the type of function. Okay, let's talk about the success criteria for today. So the first one is determine through Desmos the roles of the parameters a, k, d, and c. So we just did d and c. And functions of this form, y equals a times f of k of x minus d, and a bunch of closed brackets plus c. So I know this is a little convoluted, this expression here, but this is showing all the different transformations which are represented by these letters a, k, d, and c. Those are all the transformations that can happen to some function f. Okay, when you look at this equation, you actually don't know what the function is. We just know what we're doing to the function with a, k, d, and c. What function is this related to? Well, it might be a simple function like this, f of x equals x, which remember is just a straight line, like y equals x, y equals x. It could be f of x equal to x squared, just our basic parabola. It could be our 1 over x, which is the two branches and has the two asymptotes. Or it could be a root x function, which just looks like this, square root of x. So what happens is when these transformations are present, they're just going to have an effect on the base function. And we'll be able to actually determine what that effect is and get the new graphs. So when we get really good at this, we can then look at complicated equations or functions and we can say, I know what the base function is and I understand the transformations that are happening to it. So I know what the end result should look like. And that takes a little bit of time, but I promise you guys you'll get good at it and you'll be really good at graphing. And once we have our graphs, we can then answer, other questions about them, such as like stating the domain and range for the transform function, and maybe even applying it to some applications. So one other thing I'm going to add, this, for the next 4 lessons, we're going to be doing all sorts of different transformations. Today, we're just focusing on the horizontal and vertical translations. But these rules that we're going to learn, they apply for any function. So, if you end up taking grade 12 math courses or math courses in university, you're going to learn new functions. And all of these rules that we're going to learn in this class, in this chapter, they're going to be applied to all of those. All right, let's get started. We're going to fill out a couple definitions and then we'll do our first example. So transformations, I've mentioned that word quite a few times now. A transformation is just a change to a function so that it changes in shape, we'll say. I was thinking like shape or size, but the shape can change. It can get distorted and it can also get larger or smaller. So transformations can do that. They can also just cause a change in position. So they either cause a change in shape or a change in position. So the ones that we did in the investigation, those were just changes in position. Notice the As the slider was turned on, the parabola just moved left or right. It did not change shape. So a translation is a type of transformation that the function only undergoes a change in position. Okay, that's it. No changes in shape. All right, let's apply some of these rules to this example. So it says here, given the graph of function f of x, so here's f of x for this one, and here's f of x for that one. So I'm just going to label those, call them both f of x. Okay, so given the graphs of f of x, sketch the graph of g of x by determining image points for any original key points. So I call this process point mapping. So what we're going to do is we're given an equation for g of x. And notice it's pretty simple. It just says take f of x, which is this graph here, and add 2 to it. Okay. Notice this is like my value for c that we did in the investigation. So, and you remember if c is greater than 0, it shifts up. And if it's less than 0, it shifts down. Well, we have plus 2. So we have c equal to 2. So therefore, this is going to, we'll say, it'll be a vertical shift up 2 units. So that's all that this plus 2 means. So I want to go ahead, I want to graph it. So it says here, it says graph it though by determining image points. So what that means is I can take some original points from the graph, the ordered pairs here, and I will just apply the transformation to those points. So let's go ahead, let's write out our original points for f of x. So for f of x, I can copy them down. Starting with this one on the left, it looks like x is -3 and y is 1. So we have -3, 1. I'm just going to go ahead, I'm going to copy these for the rest. This one is -2, -2. And this one is 1, -1. And then we have 3, -1. Okay. So we're now going to apply the transformations to these points to get new ones for g of x. So I'm going to write out g of x in red here. So notice the transformation. All it is a vertical shift up 2 units because c is positive 2. So that means x is not going to change, just the y values are going to change. So in my new table of values, I'm going to write x, and then I'm going to write y plus 2. So I'm doing this so that I get the vertical shift up 2 units. So this is real easy. I'm going to take the -3 from that function. I'm going to write it in here. And then I'm going to take the 1, and I'm going to plug it into y. I'm going to have 1 plus 2, which is 3. So I now have a new point, -3, 3. Notice that would be right here on the graph. So I've taken the point -3, 1, and I bumped it up 2 units because it's a vertical shift up 2, and I get the new ordered pair, -3, 3. Okay, I'm going to go ahead, I'm going to plug these into over here, and I'm going to calculate the new ones. So x is -2, y is -2 plus 2, and I get 0. So that'll be -2, 0 on the graph, which will be right here. Notice you can see the distance of 2 between those points. Working with the next one, 1, -1, I'll have 1, plug in -1, and I get positive 1. So I'll have 1, 1. Also 2 units. Plug in 3 for x, and then plug in -1 for y. We'll have -1 plus 2, also 1. Okay, and that makes sense. These have the same height, so these are going to have the same height. Okay, just draw some lines through, and we will call this one done. Okay, we're going to label it g of x. Okay. So going from here, taking the original points and getting new image points is a process that I call point mapping. It's really easy to do. So um, now you might say, okay, well, I could have just bumped these all up too, Mr. A. That's not really that hard. Like I could have easily got the graph without doing any of this. And yeah, that's true. But um, what happens when we do more than one transformation? So what happens if there's three transformations happening all at once? Are you going to do one at a time, draw this, and then draw the next one, let's say, and then do the third one? So that's a lot of graphing that you have to do. It's better to just convert all your points over. So what I do up here is I always write in what I'm doing to the function. So here I can clearly see I'm just moving the y values up 2. So this is just a vertical shift of 2 units. If there were other things that needed to happen, I would include them in as well. And we're going to learn how to do those as we do more examples. So we're almost done this question. Actually, yeah, this is good enough for now. This question, they just wanted us to graph. So um, that's all we need to do for those. So let's move on to the next one for B. So my new function g of x is going to be f of x plus 4. So again, this is an internal transformation because we're changing x before it gets processed in the function. Okay. So here's my function right here. And this is kind of what we're doing to it. So I know that from the investigation that this is my value of d. Okay, remember it had the form f of x minus d. Well, if I compare this plus 4 to this minus d, that means that d is negative 4. Okay, so d is always going to be the opposite value of what you see inside the bracket. So how does it work like that? Well, take negative 4, plug it into d, and you would have x minus a negative 4. Well, that's going to give you x plus 4, which is what we have here. So d will always be the opposite of how it looks inside the bracket. So if d is negative 4, that means we have to shift left 4 units. So this point here is going to move out 4 to right here. Okay, this point 1, 1 also moves over 4 to right here. Okay, and I can do that again with this one here, 4, 2, that would move over 4, so that would bring it exactly to right here. This looks like 9, 3, that's going to move over 4, and that would go to right here. Okay, so notice, yeah, I just kind of did this transformation without doing the point mapping. Call this g of x. So I'll show you what the point mapping would look like. And I do recommend you always do the point mapping. So we'll first write down our original points for f of x. This is our original graph. I want to grab all those ordered pairs that I have right here. So I just write f of x. And you can write it as a table, or if you want, you could even write them as the coordinates. Okay, so I'm just listing all those points, 4, 2, and 9, 3. And these now are going to be transformed. Okay. So we're going to have a horizontal shift left 4 units. Let's write that down. I'm just going to write that right here. I'm going to say horizontal shift 4 units to the left. So in order to get my points to move to the left, I should change x. So my new points are going to kind of follow this form for g of x. They're going to follow this form here. We're going to take x and we're going to subtract 4, and we'll keep y the same. That way, we're doing a shift of 4 units to the left. So all I need to do is take my x values and plug them into x, and I'll get all the new ones down here. and then I'll take the y values and I'll plug those in for y, and that's going to give me all my new ordered pairs. Okay, let's do the first one. We're going to take x is 0, and we're going to plug it in for 0 there. So we have 0 minus 4, comma, and then we take the y value, and I'm going to plug the y in. That's just going to be 0. So this point mapped over to this point. I should actually put the value in here. Right now it says 0 minus 4, so I'm just going to erase this. And we can actually see it's just negative 4, 0. Okay, let's plug this next one in. We're going to plug 1 in for x. We have 1 minus 4, that's negative 3. Plug in our y value, negative 3, 1. Okay, let's do it again. Take 4, plug it in for x. We're going to have 4 minus 4, that gives us 0. Take 2, plug it in for y, and we just have 2. Take 9, that's our x value, plug it into here. 9 minus 4 is 5. Take 3, plug it in for y, and we get 3 here. Let's write that in. So notice, like, this is kind of like an algorithm. It's a rule that we have to follow. So we take all these points and we plug them into this rule here. The x's go with x, the y's go with y. And by doing that, we're creating all the new points. So this is called point mapping. I noticed those points really do line up with the function that we plotted. So 5, 3, that's this guy right here. 0, 2, that's this one here. Negative 3, 1, that's this one here. And negative 4, 0, that's that one there. So that's how the horizontal translations work, the horizontal and vertical translations work. Okay, I'm going to pause the video right now, and I will see you in the next one where we're going to begin example number 2.